Yeah, uh, we yesterday we started to talk about the processing of time series, and this is the last topic for this course. So what we did so far, we looked at a rather wide range of topics within machine learning, and altogether, um, I mean, you should be equipped now with quite advanced set of tools. Um, We talked so far about vectorized data. So you have, so you describe your phenomena that you want to learn about and find some patterns as a set of static features. So you have feature vectors, and so you try to figure out importance at the end. So it's all about um, finding a function that maps this input into another domain of categories. For example, if you talk about classification task, or doing yeah maybe for seeing possible clustering of the data. So here we talk about time series. So we talk about phenomena that exhibit variation in time. And in general, we talk about continuous signals, but very soon we converge to discretized and quantized version. So we split our timeline into some discrete intervals, measure the amplitudes of a signal, and again, so in many cases we map this amplitude into finite set of levels, so quantization levels. So what we have then, we have a sequence of values on which we want to perform certain, which we want to use to create a data model for solving a particular task. And these tasks are classification, anomaly detection, regression, so prediction of what would be the next value and such. So that would be the last slide from yesterday. So what we talked about a set of methods or which is based on extracting or engineering features out of this time series. So in the simplest case, so you can take your time series, and you can compute some basic statistics, mean, max, mean, and use it as an input to your model. Sometimes, so the number of features can be very large, and it can be very large by several reasons. First, because you have many measurement points which generate the data, and then each of the time series can be described by in multiple ways. So, and that was an example with, for example, extraction features in heart in the heart rate signal. So today we will talk about different approach to time series processing, which is based on usage of neural networks. And here we have two different kinds. But before, so we have neural networks based on backprop algorithm for training. So the backprop we learned during the last module in quite some math details. Here we will look at on a rather high level. So what are the problems there connected to backprop-based learning on time series, but also we will look into a different class of neural networks, which is recurrent neural networks based on the concept of reservoir computing. So that's what you will work with in Lab 6. Is there any of you who even started to look at Lab 6 or have ambition to look at Lab 6? Let's put it this way. Yes. Yes, you can. I really encourage you to do that. At the end, I can tell you that the final code is quite compact. So it's the time-consuming part is to parse the specification and map it. But I mean, when you will arrive to the final implementation, you will see that it's maybe about 100 lines of code, not more. But let's talk about the general methodology to. Okay, so now people in Zoom will start to complain. I know. I need to find my. So use slideshow, and now I need to reshare. Stop share, and I need to share it again. So I hope you see my slide. So general methodology.
Yes, we can see it.
Okay, good. So we are talking about a kind of model that we will build, so neural network, for which we would take some data from the past, and we want to we want to do different stuff. So we can use it to predict a label. So in this case, we talk about time series classification, or we want to predict what would be the next values of this signal at future occasions. So as it is exemplified here, so the input. So now we will focus on the second type of problem. Sorry. So you observe time series for some time, and then you input it to the model in order to predict some values into the future. And here, the concept that we use in general is, well, you either have a certain, a fixed length of a time interval during which you observe your time series, and you try to figure out what would be the prediction, or so basically you try to kind of look at the entire periods or at larger periods of your signal. Or the most common way of working with time series is to use the concept of sliding window. So you have a shorter time interval from which you take the data for training and prediction, and then you move this construct and use the data within this window at certain time offset, and et cetera, until you cover the entire data set. So, in this case, in any case, with the sliding window approach, so your data set construction is exemplified here. So you still have number of samples, I mean, for a given window, and then the prediction value that you're interested in. Several concepts we can define in this context: time lag, time horizon, and recursivity. They are exemplified. The time lag and time horizon are exemplified here on this graph. So we have time series. so the discrete time interval and some variable that we monitor. Um, and time lag means uh, the number of time steps uh, between the observation and the predicted value and the future value. So basically the uh, oh, I'm stuck. Just give me a second. Um, huh? Yes, yes, that's correct. And I just, somehow distorted by these things over here. Let me just remove something weird. Yeah, yeah. So, how many values you have to monitor in the past in order to predict some values in the future? And then the horizon basically means how far in the future you want to do this prediction. So that's uh, the thing. So, yes. So we with time horizon we define the scope of prediction. So how far in the future we can look. Um, Recursivity means that whether we use or not the predictions um, for predicting the new values. This can be exemplified here. So this is our time series. So indexed back in time to from the step -1 to n. The number, the size of the window we take for the prediction, and so we make a prediction until I mean for the next time step in this case, and so the recursivity in the prediction means that we take the next predicted value for predicting the other one. Whether the non-recursivity means that we need to train separate models to kind of so based on the training data that we have, so to predict at certain time horizon. Then when processing time series, important is the method for um, training your model. So which data is to use for training and testing. So unlike the vectorized case, so we here we cannot split the data in the same way into, say, testing, validation, and in the training, validation, and testing set. So we need a method for evaluating a different method for evaluating the performance. Uh, uh, so when applied to the actual data. And here we have different approaches on how you do. I mean, they are good for some specific cases. But you need to be aware of them. So first so if we have data sets, so now each of the column here corresponds to time step. So we have a fixed, so we define part of the data set, so a certain number of time steps for the training. And then the rest we use for validation or for evaluation of model performance. So the obvious limitation is that with this approach you do not account for possible variation of the model in the future, since you don't include this future data in your evaluation process. So so it works like this. So you fix the certain number of time steps, train the model, and then you test it on all subsequent time steps. Another approach, which is common in processing of the time series, is called refit and retrain. So here you see that we use a sliding window to slide through the available data, and we use always new data for training the model. So the training window is fixed, and then we roll it forward in time to and test on the future. So in this case, the model accounts for possible variations beyond the original scope. So graphically, it works like this. Again, all these approaches you can try even for lab 6 when you do the training. Also, it's not explicitly mentioned, so that you have to try different variations. Wait a second. Yeah, so here the difference is that I always increase the training size. So and your model kind of includes all the data as you propagate forward in the future. Again, exemplified here. What would be the benefit of using that, or because yeah, that's a great question. What is the benefit? I mean, to answer this question, you need to look from two perspectives. First, compare. I mean, having a longer span of data, so you may account for long-term dependencies in the signal. So I mean, that your signal might experience. So some really far away data may affect the predictor in the future. But the other aspect of this question is the computational complexity. So how much memory you have, and yeah. A good thing about the sliding window way of training, because then you can have a sensor with limited
storage space to be able to, well,
Yeah.
training, keep updating its model.
Absolutely. So if you talk about online training, yes, that's it. So if you again, if you talk about kind of offline training, then you have the whole data recorded already. And then again, so it depends on how big this data is to be able to, and whether you have resources to train. So maybe I can refer to a case not immediately connected to signals, but rather to language. I mean, if you have very long input, so compared to smaller context window that you slide. So the trade-off is between the accuracy of prediction, so the context which you take into account, but also, I mean, the larger is the context, the more complex is your model. So then, again, evaluation. So this section is really specific to time series derived from signals. So we want to measure the quality of the model, of the predictor. So we can use different measures from statistics, like sum squared regression, R square, or other measures as summarized here. So you also can have a look at this source for more concrete definition. So again, in general, I mean, it's not a goal with this class to go into specific details of these measures, but you can, I mean, some standard metrics, for example, mean absolute error or mean square error. That's that I visualize, yeah, and as well as RMSE metric. So the difference is this is that these metrics are scale dependent, while these type of metrics are uh, well based on percentage of error. So it's a scale independent. So mean absolute percentage error defined in this way. Um, And what I'm saying is, I mean, the main message is that, I mean, one straightforward way of assessing quality of the predictor is to plot your predictor against the ground truth. And however, I mean, maybe you can get some first impression, but this impression, unless you use proper metrics, can be misleading. So the signals can be, I mean, maybe they repeat the shape, but I mean, they can be misaligned in time. So, and that's, I mean, according to the metric, you can, so, so using the metrics, you can qualitatively decide on that. So, let us now talk about two kinds of neural networks, the network based on backpropagation in time and randomly connected neural networks based on the concept of reservoir computing. So here I mean, we are using classical feed-forward networks as we considered during the last two classes, to process time series. So we input in the prediction manner. So we use a sliding window to input the values. So several hidden layers, and here we can have variations. So we can have one or several outputs at the end. So it can be one-to-one mapping. So basically, a single time step. We can train a network to predict, say, for a single output, one to many, many to one. So that's many to one is more about. So in this regime, we talk about signal classification. Many to many, so the predictor, and which is suitable for online classification of streaming data. And however, the classical feed-forward networks, they need to be the pipeline need to be adjusted, and in particular, we need to introduce some internal state. So we need to implement the recurrency. So the network should incorporate the state at a certain point for computation of the state at the next point in time. But the general formulation is, I mean, can be expressed by this simple formula. So we have, so this is our activation function. We have the old state and the current state, and that altogether contributes to computation of the new state in the neural network. So practically, so this activation is again is a nonlinear activation. So tonnage, sigmoid, or similar. There is and maintaining of separate set of weights for the current input and the transition between the internal states in time. So what is happening here? I mean, the classical way of working with time series. So you basically you can see you can think of it as unrolling the time series in time, and feeding in the state of the network from the previous state to the computation of the next time step. And you assign the weight to these computations from the input, and at the end, so you want to evaluate the error of prediction, so which is loss function at the end.
你找对这样啊，理解。Box me.
No, okay. He muted himself. So all in all, so learning from time series, again, I'm not talking now about transformer architectures. They use a slightly different principle there. Also, maybe I need to include it for the next incarnation of the course. But the vanilla recurrent neural network can be seen in this way. So you, as I said, you unroll it in time, you see, and you basically have a kind of feed-forward neural network with cross connections between states, and you evaluate a loss function at the end. The main problem, yeah. So for computational reasons, you want again do the processing on portions of data, because for computational, but also in I mean for some specific use case, when you probably know that there is no longer dependencies in the signal. So you can implement truncated learning, so using backpropagation through time. So one of the serious problems connected to vanilla recurrent neural networks is a problem with learning, with the backpropagation itself. And specifically two problems of vanishing gradient and exploding gradient. The vanishing gradient refers to the case that during the backprop, so the values of the gradients are very, very small. So the so that you basically don't introduce any learning. And the exploding gradient is the opposite, obviously, event. And there are different measures you can apply to mitigate this gradient, but it's still training recurrent neural networks was and is or it can be quite complicated. So here are is the summary of different manifestations of vanishing and exploding gradients, so which you can use practically. Talking about reservoir computing, it's a concept which is well, it was invented to mitigate the problem of vanishing, exploding gradients, and it is based on a different principle. So the principle behind reservoir computing is that you have a dynamically changing part of the network, so in time, and then you have a trainable output. So it has, maybe it sounds a little bit confusing in the beginning, but what essentially is the idea behind this method is that, so you have each value that you supply to the input introduces introduces kind of unique nonlinear modifications to the activations of neural network. And that's okay. So what you try to learn, you try to learn kind of patterns in this modification. So you don't care about fine-tuning the weights between the neurons, but rather you want to see how these disturbances introduced by input can be captured by the final leg training. So and the final training is normally linear. So you want to map from the different states of your dynamically changing activations in neural network, well, with recurrent connections, That's important. And here you have options, either to set of a finite set of categories in the classification regime, or to the desired output value on a certain time horizon. So this is the idea that you will be working with in lab 6. So you have a set of inputs. It can be one, so I mean, or it can be several. So this you can see as, I mean, each input you can see as separate channel, a sensor channel, and this is the neural network that kind of lives, you know, in a very non-technical language, it lives its own life. So it has certain connections between neurons, random connections, actually, initially and throughout the runtime. And what it does, so we need to define the update rules. So how we blend in input in with the current state of the network. And what we do, we record these states. So for each input, we record so how the state of the network was modified. So sample by sample by sample after sample after sample. And at the end, we have a long matrix. So with the n, well, let's put let's agree with notations here. With t rows, so corresponding to the time steps that you blend in, and n columns where nr, where nr is the dimensionality of the reservoir. So basically, the number of neurons you have in here. Yes. And as such, so the first thing you have to do, again, so on this figure, I want to explain it by hand waving, basically. So you have some number of inputs. It can be one and one bias. But in general, you can have just a single source of data. What you want to do, you want to first to project it to the size of the reservoir. So basically, you want to project this low dimensional input onto high dimensional reservoir, and you do it with W-in matrix. And what you do here is the projection to high dimensional space. So, and as I told you, I mean, this HDC stuff that I have presented to you, so it's nothing new in this respect. So projecting into high dimensional space, so you kind of, well, you align the dimensionalities, but you also, well, preserve the similarities, the original similarities of the input. But basically, projection is aligning the dimensionalities, so that's what you do. And then, as I said, you record. So for each time step, n, a small n, you record them. You record the actual activations of this reservoir. And there is an equation that governs the updates for each step. And at the end, you need to do the opposite mapping. You want to do the mapping from all the patterns that you observed in your reservoir down to, and now again, so that you have two options. Either down to n finite number of categories, or to number of predictions in time. So so how many steps you want to do prediction, and this is the thing that you learn W out. So this W in the projection matrix is fixed. This W hat matrix, so the which is responsible for weights between these connections, is fixed. V out is learned. And here we have a variant of the update procedure for the reservoir. So what we have this projected input, so W in matrix multiplied by low dimensional input sample at time n, and you blend in with the state of your neural network at the previous time step. So and this is the where recurrency is happening and the dynamics happening. So every time you have your weight matrix and you multiply with the with the x, the states, so you enable the information flow between different neurons with different weights in between them. So here within the reservoir. So every time you take the previous activations of so basically the values after computing the activation function in each neuron and apply and multiply with this matrix, you actually well, permute is not a correct word, but you enable the dynamic. So you make it as appear as a new state, and you use it to blend in with the current input. And as I have already commented, for the output, so you have V out, which is unknown, and you use the recorded state of the reservoir for n steps. The important, everything is fine, but I mean, the very important is to assure certain properties for the W hat matrix, which is responsible for dynamics of update. So how values are transferred within the this recurrent neural network. And speaking again on a high level, description, your network should eventually forget the values that it had in the past. So they need to be substituted by newer input. So and this is the this is called the so accounts for forgetting effect. And and that what I said is I mean this property is behind the intuition of a reservoir computing. So your input should result in a unique signature of the network activation somehow, and then collectively these unique signatures. So you I mean hopefully so the signals within certain categories so they experience same patterns. That's why you can train the V out matrix. And there are several mathematical properties that you need to your weight matrix needs to satisfy in order to enable this behavior. So the main is the assurance of the spectral radius. So spectral radius, again, without going into the math of matrices, so you basically ensure that the largest absolute eigenvalue is no, the spectral radius should be 1. That means that it should be scaled down, scaled by the value of the largest absolute eigenvalue, which is described here. So you start with some randomly generated matrix, you compute the eigenvalues, and you scale by, I mean, for the target one. The training phase, let me skip this slide, is linear. So you basically have, as I said, set of recorded reservoir states, and on and in parallel you have the desired output, so which is y target. And if this matrix X, so if you is invertible, it would be invertible. So you would, I mean, there would exist inverse matrix. Then B out is simply so you take the desired outcome y vector or matrix and multiply by the inverse matrix of the reservoir state. But as you imagine, and as you know, so not every matrix is invertible. I mean, in an analytic form, but you can compute a pseudo inverse value. And so that's one of the way to train V out. So you can you compute the Moore-Penrose pseudo inverse inversion and multiply with y target. Another, which is widely used method, is to use rich regression, which is which uses the regularization coefficient in the training. So this is an extra hyperparameter that you have to tune for best performance. And so importantly, I mean, since you don't entangle the state of the network with the specific output, so the same reservoir can be used to train different readouts matrices. So depending on the task you want to solve. So for predicting the next value for classification, for example. In the regression case, so one addition you need to do here, what you want to incorporate possible output here. So you can use the prediction to as part of the input as well. So you can include the feedback from the output in the reservoir state. And I think, let me see. Yeah, so these are the set of hyperparameters you have in this concept. So as you will see, it's I mean the training is not very complicated. So during lab 6, so that will be the rest is for your self study basically. Yes, and that is it what I have for today. So if we just look back what we have covered, so we had 6 modules. We started from some basics or fundamentals of machine learning, and the important message, if you remember, is the pre-processing and the systematicity in using data sets for tuning hyperparameters. We moved on and talked about natural language processing, right? Yes. Or rather talked about different ways for coming up with word embeddings, which is an important concept. And my message with this course is, again, just to recapitulate. So you can solve many tasks with artificial neural networks. They are capable and they can do cool stuff. In addition, so you shouldn't forget about alternative methods, which could be more computationally efficient while achieving same performance. And then we had one module talking about, well, specifically my research area. And here my message is when working with machine learning, so it's always good to have this intuition of working in high dimensional space. So that is what we do. I mean, our data is always high dimensional, and we try to find certain regularities in data in this high dimensional representation space. What I do with this, or what we can do with this framework of high dimensional computing, we have tools to modify the properties of representation. So we can construct representations on the flight and on the fly, and that is in strong contrast to the way how compositionality is implemented by artificial neural networks. So I look forward for your presentations on the seminars, and I hope already now you read this paper and discovered the challenges there. And then we had this self-organized maps, useful technique to have. If you want to know more, so there are variations of it, so more kind of discovering dynamically the manifolds. Manifold learning, we didn't talk about it, but if you are interested in this direction, so there are a great deal of problems and solutions in the unsupervised context. So how you can characterize these complex shapes that's in high dimensions that can be projected to lower dimensional case, because in many cases high dimensional data can be projected on lower dimensional manifold. Simple example, so MNIST images, the raw data is high dimensional, but at the end we are talking about 10 classes, so it's the dimensionality of the manifold is lower. So how to analyze it and how to project it, so that's still active research topic. And finally, backprop, just briefly, with the focus on internals of implementation. So when we and the takeaway message is be aware about the particular combinations of cost functions that you use at the end. If you ever come to the need of implementation of such or similar protocols. And finally, we can conclude it with the processing of time series. So, and here again, on the contrast, I wanted to show a neural network-based approach versus a reservoir-based approach. So reservoir-based is very capable, and it's a way more lightweight solution for many practical tasks. So that would be my final message. And that's it. So you have, well, a couple of labs, more seminars starting this Friday. And that's it. Yeah, if you have questions, you're always welcome to write me.
Thank you.
Yes, thank you.
Thank you, Evgeny. Can I ask a few questions about the seminar?
Yes, please.
Yeah, so I wanted to ask, I am not sure if you mentioned